Okay, folks, here we are at 8.2. We're going to be talking about tangents. We talked in the last section about secants, where a line intersects a circle at 2 points. Now we're going to be talking about it where it intersects at 1 point. And if you picked up on 8.1, we talked a lot about some right triangles inside the circle with those chords. And now we're going to be talking about right triangles that are outside the circles, or most of the right triangles will. So hopefully you can follow along, take your time, listen to the video again if you need to. So here's our definition. A tangent is a line in the same plane as a circle that intersects the circle in exactly 1 point. So I'd like you to pause the video right now, and if you can, name some tangent on this circle. So the tangent is line HF or line GF, right? And the point of tangency is, it is point F, right? For circle O, point of tangency, as opposed to M and N, which is a secant. Line HN, line HM is a secant, all right? Tangent comes from tangere, Latin word that means now a tangent segment. A tangent segment is a segment of a tangent line that contains the point of tangency. So again, I want you to pause the video and name for me a tangent segment. So GF would be a tangent segment. What's another one? HF, DF. All right, here's our first theorem. If a line is tangent to a circle, then it is perpendicular to a radius drawn to the point of tangency. If a line is tangent to a circle, then it is perpendicular to a radius drawn to the point of tangency. And they prove this here at the bottom of page 351 with an indirect proof. So given line AB is tangent to circle O at point A, prove that OA is perpendicular to line AB. And so the first thing we do in an indirect proof is negate the proof, what you're trying to prove. So assume that segment OA is not perpendicular. And so therefore we find a point X, where X is an element of segment AB, line AB, that is perpendicular to AB. Since the shortest segment from a point to a line is the perpendicular segment, therefore OX would have to be less than OA. The chord postulate then implies that X would have to be on the interior of circle O, making line AB a secant, which intersects a circle in 2 points. But we know that that can't be true because we were told in the hypothesis that line AB is tangent. So therefore the assumption that line OA is not perpendicular must be false, and therefore we prove it's true. So again, this is an indirect proof for this theorem. Now, we can turn this around to get our next theorem. If a line in the plane of a circle is perpendicular to a radius at a point on the circle, then the line is tangent to the circle. So again, this is just the converse or the corollary of 8.21 is 8.22. All right, so now we're going to work out an example. Find the measure of each angle in quadrilateral ABCD if segment AB and segment AD are tangent. Now the theorem tells us that because they're tangent, therefore the radii are perpendicular. So CB has to be perpendicular to AB, and that of course is going to give us what kind of angles? It's going to give us right angles. So therefore what we're looking at here is a kite. right? All right. So first of all, the measure of angle B has to be 90 degrees because CB is perpendicular to AB. The measure of angle D is also 90 degrees because CD has to be perpendicular to AD. That's what the tangent theorem, the first one, tells us. So therefore, we can now use the total of the measures of angles in a quadrilateral to get the answer. So we subtract 180 from both sides. So 4x equals 180. Therefore, angle A has to be 45 degrees, and we multiply that by 3 to get measure C, and we get 135 degrees. Now, if you are given a circle and a point in the exterior of the circle, you can construct two tangents to the circle. And this is the new construction that you're going to have, and you're going to have this on your quiz number 1. Now, this construction takes 9 steps. 9 steps. Most of them are simply that you have to bisect a segment connecting the point and the center of the circle. So here, given circle P with point X in its exterior, construct ray XA and ray XB tangent to circle P. So again, 9 steps. So here we are with our circle. Here's our point X. And as I said, the first 6 steps are simply that we're going to have to bisect. So there's step 1 is we have to connect P and X. Now we have to bisect this. So we've got 2 clicks from point P, and then we have to do the same distance to find these 2 points. Now we connect those 2 points. So we're up to 5 steps. There's your 6th step. That bisects PX at point M. Now we do step 7. So we place our at point M, the length of point MP. That gives us 2 points of tangency on the circle at points A and B. So now all I have to do is take my straight edge and draw a line or a ray from X to A. That's step 8. And I do the same thing to B. And now I've completed this construction. This construction will be on your quiz, so please practice it several times. All right, here's our next theorem. Tangent segments from an exterior point to a circle are congruent. So what this is telling us is that segment AX is congruent to segment BX, or length AX is equal to length BX. And of course, if you remember the first theorem, you know that PA is going to be perpendicular to AX, and PB is going to be perpendicular to BX. And of course, that means we're going to have nice congruent right triangles there, which we'll talk about. So here's the proof. Circle P with exterior point X, segment XA and segment XB tangent to P. So we use the line postulate to draw segment PA, PB, and PX. We know that PA is congruent to PB. Why? Because all radii of a circle are congruent. We know that PA is perpendicular to segment XA, segment PB is perpendicular to XB. Why? Because of the first theorem. A radius to the point of tangency is perpendicular to the tangent. Therefore, angles PAX and angles PBX are right angles. Definition of perpendicular. Therefore, triangle PAX and triangle PBX are right triangles. Definition of a right triangle. PX, we know, is congruent to PX. Why? Because of the reflexive property. Therefore, triangle PAX is congruent to triangle PBX. Why? Well, if these are both right triangles, and PA is congruent with PB, and PX is congruent with PX, which is the hypotenuse of these triangles, therefore the hypotenuse leg congruency proves their congruence, and therefore we can say that AX is congruent with BX because of congruent parts of corresponding parts of congruent triangles are congruent. Our old friend CPCTC. Okay, when a circle is inscribed in a polygon, each side of the polygon is tangent. That is, the circle is inside the polygon and it's touching each side only at one point. The polygon is said to be circumscribed around about the circle. So inscribed means written within, and circumscribed means written around. So the polygon is outside the circle, but it's touching each side at one point and tangentially. So our next example, find the perimeter of circumscribed quadrilateral, or drawn around PQRS. Now, QX, they're telling you, is 1.4. What do I know is the same length? QW, right? RX is 2.7. What segment do I know has to be the same length? RY. So there's a reason they only need to give you 4 sets of numbers here, because PW equals PZ, XW equals QX, RX equals RY, SY equals SC. So therefore you just double all of these measures, and that gives you the answer of 22.8 centimeters for the perimeter of PQRS. A common tangent. A common tangent is a line that is tangent to each of 2 coplanar circles. This is the definition. So here we see that line C and line D are common tangents, as are line F and line G are common tangents. But they're different kinds of common tangents. So let's look at that. All right, so let's look at these common tangents. The top one is called a common internal tangent because it intersects the segment connecting the circle center. So here we have circle A and circle B, and let's imagine a segment connecting A and B, these circle centers. And as you can see, line C would intersect segment AB, and line D would intersect segment AB. And so those are called internal tangents because they are in a sense between the 2 circles. The bottom one are common external tangents because if we draw this segment connecting A and B, the circle centers, lines F and G do not intersect segment AB. And so this is the difference between a common internal tangent, the one at the top, and a common external tangent. All right, example 3. So example 3, determine the length of a chain between the front and rear sprockets of a bike if the axles are 2 feet apart and the diameters of the sprockets are 10 inches and 4 inches. So first of all, if you look at the right, you've got the front sprocket, right? So you've got center F and tangent F. And then we have the rear sprocket on the left. And what they're saying is that the distance between the centers is 2 feet, and they want you to find the length of chain between them. So you've got to find the length of segment TF and TR, which is labeled as X. Now notice that they have drawn a line from tangent R parallel to center F and center R, intersecting TF-CF at point Z. They've also given you the radii of these circles, circle F and circle R. And they say that circle front is 5-inch radius, circle rear is 2-inch radius. So they're asking you to find this length. And what you'll notice here is that TFZTR is a right triangle. And guess what? You know what the hypotenuse is of this right triangle is. because it's the same as segment center front and center rear, which is 24 inches. So all you have to do is apply the Pythagorean theorem to a right triangle that has a hypotenuse of 24 inches, and one of the legs is the difference between the larger radius minus the smaller radius. So therefore 24 is the hypotenuse and 3 inches is one of the lengths. So you would square 24, you would square 3, subtract that, and then take the square root, and that is what is going to give you the answer. And you can find this worked out for you on page 354. And then finally, we have tangent circles. Tangent circles. Tangent circles are coplanar circles that are tangent to the same line at the same point. So I want you to pause and identify some of the tangent circles here. And of course, we have tangent circle N and circle M would be two tangent circles, circle P and circle M. So these tangent circles come in two types. The one at the top, internally tangent circles are on the same side of their common external tangent line. So pause the video and ask yourself, what are the two internally tangent circles? And they are, of course, circle N and circle M. They're both on the bottom side of the external tangent line. Then we also have externally tangent circles are on opposite sides of their common internal tangent line. So again, pause the video and ask yourself, what are some of the externally tangent circles? And in this case, you've got two choices, circle P and circle N, or circle P and circle M. So these are internally tangent circles, M and N, externally tangent circles, P, and either M or N. All right, so I want you to do 2 to 32 even, and when you get to 32, look back at example 3 to help you. You also need to be prepared for a quiz on Friday, and this quiz will include the new construction on making tangents to a circle from a point outside the circle, and that's going to mean it's 20% of your grade, so please make sure you're practiced and prepared for that. All right, folks, God bless you. Let me know if you have any questions, and I hope you do well.